Good morning, everyone. This is Saujanya, working as assistant professor in CSE department in GRIT. Today, I'm going to explain Hadoop distributed file system. Hadoop distributed file system is one of the core component in the Hadoop. In today's class, I'm going to explain about design of Hdfs as well as the concepts of Hdfs. HDFS is a specially designed file system for storing very large files with streaming data access patterns running on cluster of commodity hardware. Let's examine this statement in more detail. Very large files. Very large in this context means files that are hundreds of megabytes, gigabytes, or terabytes in size. There are Hadoop clusters running today that store petabytes of data. Streaming data access. SDFS is built around the idea that the most efficient data processing pattern is a write once, read many times pattern. A dataset is typically generated or copied from source, then various analyses are performed on that dataset over time. Commodity hardware. Hadoop does not require expensive, highly reliable hardware to run on. It's designed to run on cluster of commodity hardware, commonly available hardware. Now, where we cannot use the Hadoop or SDFS. SDFS does not work so well in these three situations. When we are having that low latency data access, or lots of small files, or multiple writers, arbitrary file modifications. In these three situations, we can't use that SDFS. Next, SDFS concepts. In this one, first concept is blocks. A disk has block size, which is the minimum amount of data that it can read or write. File system for a single disk built on this by dealing with data in blocks. File system blocks are typically a few kilobytes. Disk blocks are normally 512 bytes. HDFS has the concept of a block, but it is a much larger unit, 64 MB by default. Like file system for a single disk, files in HDFS are broken into block sized chunks which are stored as independent units. HDFS blocks are large compared to disk blocks, and the reason is to minimize the cost of six. Benefits for block arbitration. A file can be larger than any single disk in the network. To store a single file on HDFS cluster whose blocks filled all the disks in the cluster, making the unit of abstraction a block rather than a file simplifies the storage subsystem. The storage subsystem deals with blocks, simplifying storage management and eliminate the metadata concerns. Blocks fit well with replication for providing fault tolerance and availability. To ensure against corrupted blocks and disk and machine failure, each is replicated to a small number of physically separated machines. We can see this is one of the syntax which will be used to know how many blocks the files will be stored. Next one is name node and data node. HDFS have five services and the name node and data node are two services available. HDFS cluster has two types of node operating in a master worker pattern or master slave pattern. Name node we are calling as a master node. Data node we can call it as a slave node. The name node manages the file system namespace. It maintains the file system tree and the metadata for all the files and directories in the tree. This information is stored persistently on the local disk in the form of two files, namespace image and edit log. A client accesses the file system on behalf of the user by communicating with the name node and data nodes. The user code does not need to know about the name node and data node to function. Data nodes are the workers of the file system. They store and retrieve blocks when client required, report back to the name node periodically with list of blocks that they are storing. Without the name node, the file system cannot be used. In fact, if the machine running the name node were down, all the files on the file system would be lost, since there would be no way of knowing how to reconstruct the files from the blocks on the data node. The name node resilient to failure, and Hadoop provides two mechanisms for this. One is backup file system metadata in the multiple file system. To run a secondary name node, the secondary name node usually runs on a separate physical machine. This is a Hadoop architecture. Here we are having the client will send the data to the name node. The name node will verify the data whether existing file is available in that Hdfs environment. If it is not available, the client can store the data in the name node. The data which will be stored in the name node in the form of metadata. It's nothing but name, replication factor, and like that of this address will be there. And here the data nodes. Name node will store the metadata, whereas the data node will store the actual data. The client can read and write the data from the data nodes with the permission of the name node. Here we are having the racks, each cluster having the only one name node, number of data nodes. Normal SDFS architecture. For suppose if you are taking the one Hadoop file system, the client application is here. If the client wants to store the data in the name node, this file is name is sample.txt. This will be stored in the three replication factors block A, block B, block C. Right? That after that the data will be stored in the different data nodes. Like this will be there. Just now I said that name node will be stored in the two files, fs image as well as edit log. Fs image is also called namespace image. Here file in which entire file system is stored in the namespace image. Edit log will store the records every transaction that occurs to file system metadata. Right? Then how that data node and name node will be communicated. The master node name node will store metadata about the data, right? About the data nodes, right? So always data node will send heartbeat message to the name node because that is in running state or not. Okay, thank you.